Thank you. Hi everyone, my name is Meghana and I work with Swarat, Chaudhuri and Tom Dubs, and this is a work called CFLOBDDs, context-free language ordered binary tissue diagrams. So what are these? It is a data structure to represent enormously large sets, vectors and matrices very compactly. So what do we mean by that? Let's say we have a set consisting of 2 power n elements. In the best case, we expect CFLOBDD to represent that set in an O of n size. That is, it can provide a double exponential compression. So you take large vectors and matrices, and depending on the structure, CFLOBDDs can provide a good compression. So where do we see such large vectors and matrices? One such area is quantum simulations. So we use CFLOBDDs to represent quantum states and quantum gates and hence perform simulations efficiently. So here's a sneak peek into the results. We see that CFLOBDDs are better than BDDs on some of the quantum benchmarks, and they are as good as BDDs in case of some other benchmarks. So how do we get this? Let's see that in detail. So I'll first go over what decision trees and BDDs are at a high level, and then we'll discuss CFLOBDDs. So let us take this function of over 4 variables. This is the decision tree representation for the function. Every level here, let's say call it pi, corresponds to 1 variable, and then you have the terminal values. That are the values for the function for these particular assignments. So as we can see, there are a lot of common structures. That is, the red color highlighted subtrees are similar and hence maybe can be merged into one structure. Similarly, the green structures are also similar and can be merged. And this can be done at every level, and thereby you have a much more compressed representation. And this is the binary decision diagram representation for the same function. In the best case, BDD gives an exponential compression over a decision tree, and that is, you would have a n-size BDD for a 2 power n-sized decision tree. Why BDDs are good? They also give canonical representations, and they're computationally efficient. That is, they run in polynomial type in the size of the arguments of the BDDs. So these are good, but can we do better? And that is where CFLOBDDs come into picture. So let us take one example of a true function over 1 variable. It's not interesting, but this is a BDD for this function, and it's the same thing as CFLOBDD for this function. Let us take another example of true function over 2 variables. As you can see, this is a BDD representation over these 2 variables. Let us restructure the edges a bit and add a sort of hierarchy. And this still evaluates to the same, this still represents the same function. But as you can notice that the node corresponding to x0 and x1 are similar, and hence they can be reused and get a much more compressed representation in this sense. That is, you're using the same representation for 2 variables, and you're still not running into any cycles, because we use something called, okay, think of this particular node representing a function, and you're calling the function from 2 different call sites. And the path that you take depends on the call site that you have come from. So this is what we call the mash path principle. That is, when you enter a function using, say, a solid edge, you always know where to return. You always leave the function using the solid edge. Similarly, if you enter using a dotted edge, you leave the function using a dotted edge. And this sort of adding hierarchy and using this procedure called mechanism is what gives CFLOBDDs a more compressed representation than what BDDs can do. Let us look at a more complicated example. This is the same example that we have seen before in a very uncompressed version of CFLOBDD here. That is, you take the decision tree, you restructure the edges a bit, add a hierarchy, add these circles, which we call groupings. The decisions are still at the lowest level, as you can see, corresponding to the variables here. So let us look at one path, all true path. This is encoded as follows. You take a path from level 2 to level 1, level 1 to level 0. Take the decision corresponding to the first variable, that is x0, and then follow the path. Take the second decision corresponding to x1, follow the path, and you do this until you reach the final value that is true. This is how it looks like. but as you can see, there are a lot of common structures here, and maybe we hope to reuse a lot of these structures in this way. But how do we do it? Let's look at that in a little more detail. As you can see, a little bit of terminology here. Let's call these dots, the black dots here, as vertices, and the others as edges, these lines as edges. So these 4 vertices here, exit vertices, the first are connected to false, and the last one, the green one, is to true. You see this pattern repeating in the next exit vertices as well. And these correspond to the exit vertices of these groupings here, as you can see. And the last 4 correspond to they all map to true, and they correspond to the 4 exit vertices of this particular grouping. One can notice that there are similar structures here as well, and this can help in introduction, which we'll see now. So the first thing to do is collapse all these vertices into one single vertex and merge the edges. So we do this, we collapse all of them, all the vertices here, do the same thing for the true ones as well, and propagate this upwards into the structure. So as you can see, the 3, in this case, we would collapse all the vertices here, propagate this up into the structure, and we would do this for every internal grouping, and thereby we would merge vertices and merge groupings as well. So we have seen how we have merged vertices so far, vertices and edges. We'll see how groupings can be merged in this case. Let us take this example where you have, as you can see, there are the blue highlighted groupings are similar, and they map to the same function, and hence they can be merged, and this can be propagated upwards, and all the groupings now that are similar and represent the same function now can be merged in the same way. So we have all the groupings in the second half of this structure are now merged, have been reduced. Now, and this, well, we want to propagate this upwards, and we can see that these red highlighted groupings are same. They represent the same function over the same set of variables. And so we would now merge these nodes and again, do the same thing, propagate this upwards in the structure. Now, let's do this. We are propagating it in the same way. And now that the top part is also has been compressed, we observe that the top part and the bottom part are similar. And though they represent the same function over 2 variables, we do not condition the decisions. We do not have variables associated with a particular decision node. So hence, we can merge these groupings as well, and this would lead to a much more compressed representation. And this is what we call a CFLOBDD representation for the same function, which is much more compressed. And the path that we have seen before is now encoded in this structure itself. So all the paths, all the 2-part, 2-part, and paths that you would have are all represented in the structure. So why is it, okay, now why is it called a CFLOBDD? It's sort of a misnomer, but we named it because it follows this matched path principle. That is, you have an open bracket, do something, and then a closed bracket, and that is how the naming comes about. Oh, we have seen, okay, are they better than BDDs, and why so? Let us look at that in detail. Let us take this example of Hadamard matrix. It's a matrix over 1 variable, over 1 qubit, or 2 variables. The variable, let us take the row variable and column variable as the decision variables. And this is the BDD representation. The corresponding CFLOBDD representation is like this, where we form this by adding a hierarchy and adding the procedure called similar mechanism that we have seen before. But what is interesting is that let us take next example in this series, that is H2 chronicle with H2. And in case of BDDs, these are the representations, but look, let us think what these are. In case of BDDs, it is one H2 stacked on top of another H2. In case, let us do this for CFLOBDDs as well. We would do the same structure, but we can notice that this H2 and these H2s are similar, and hence can be reused. So we would reuse the same node, and thereby we would have a compressed representation. So in case of BDDs, as the number of variables increases, you would have a linear scale growth. However, in case of CFLOBDDs, you would always have a log scale growth. This is because BDDs, where they are acyclic programs, CFLOBDDs can be thought of acyclic programs with non-recursive procedure calls. The main benefit that we have observed so far is BDDs share DAGs, sub-DAGs, whereas CFLOBDDs share middle of a DAG, and that helps in this efficient representation. So a CFLOBDD, given this decision tree, in the best case, gives a double exponential compression over the decision tree, as seen here. So we have seen best case scenario where CFLOBDDs are better than BDDs. The next thing is, are they canonical? So to make CFLOBDDs canonical, we introduced some structural constraints so that you have only one unique representation for a given function. And are they computationally efficient? The algorithms on CFLOBDDs, they run in polynomial time in the argument CFLOBDDs or the output CFLOBDDs as well. So is there an exponential gap? We have seen that, but we have theoretical results saying there is no variable ordering for a BDD where you have a much more compressed representation. And whereas there is at least one variable ordering where CFLOBDDs have a good representation. You can look at this in the paper, but so we intend to use CFLOBDDs as a plug-compatible replacement to BDDs. That is, they can support all the operations that BDDs can do. However, they do need to, so the users do need to think about redesigning some of the algorithms because BDDs follow a standard divide and conquer approach, whereas CFLOBDDs follow a slightly different approach. They are a root and divide and conquer because they divide on the number of variables and not on the number of outputs. So that is one thing that someone needs to think about if they want to use CFLOBDDs. So now we have seen how they're better than BDDs. Can they do something good? So yes, in quantum simulations, we have seen that they give some good results. So we have tested on some quantum benchmarks. We tested CFLOBDDs and BDDs, and we observed that they give pretty good results in some cases, as much as they can represent a structure of 2 power 4096 elements, but see, a BDD would represent 2 power 32 elements. So, however, in some cases they don't. That is, let's say in this case, CFLOBDDs, both in times of memory and time, they perform better than BDDs. However, let's say something like a QFT algorithm, where BDDs do not perform, BDDs, though the number of qubits that they scale to is similar, BDDs may slightly perform better in terms of time and memory. We also tested with some tensor networks, some standard quantum simulation networks. So we observed that on some benchmarks, again, CFLOBDDs perform much better than tensor networks as well, as you can see here. But in case of some complicated benchmarks like QFT, CFLOBDDs don't perform that well. So in conclusion, I would say CFLOBDDs are good in some cases and not so good in other cases. So it depends on the application that you want. But all in all, we would want to use CFLOBDDs as a plug-compatible replacement to BDDs, where they can give double exponential compression over decision trees and exponential compression over BDDs. And one such application domain is quantum simulations. And the key idea is that they use the middle of a DAG, which actually gives this compression. And we hope to see if there are other domains as well where we can use CFLOBDDs in place of BDDs. Thank you.
Thank you for the talk. We also have 5 minutes for questions.
Hi, thanks for the talk. I had a question. The way you are choosing the patterns, is there any order in the grouping, or can I just be greedy?
Oh, it's a fixed pattern. So there are structural invariants.
No, but does it matter the order in which if I pair AB first and then CD, or if I do AC and then BD?
You mean A, B, C, D are variables?
I mean, no, it's all just graphs, right? I'm kind of merging different parts of the graph. I'm thinking of that.
Oh.
So A is a subcomponent, B is a component, C. So if I merge AB first and then CD, or AC and then BD?
If they all represent the same function, you would end up with the same representation. It does not matter in which way you merge.
So you're saying the just the greedy approach of merging whatever I find should be fine? Okay, thanks.
Hi, thanks for the talk. I have two questions. So the first one regarding, did you try to do some benchmark on standard BDD problem, like hardware verification or these kind of things?
Yes, so we did that initially. They did not scale as well as, CFLOBDDs did not scale as well as BDDs because of the extra structure invariants that had to be placed on CFLOBDDs to make them canonical. So the second point is, I think it's also because of the implementation details. So we, in the last few months, I would say, we improved the implementation for CFLOBDDs, and we hope to try those again and see if it's actually the structural constraints or if it's the implementation. So
Okay, thanks. Second question regarding quantum simulation.
Yes.
So BDD, or your kind of BDDs are very good when you have 0 and 1 on terminal leaves. But in quantum simulation, it seems to me that you could have many different numbers. Basically, how does it work if you have too many of them? Or is there some kind of relationship between the problem creating many constant values and the way that it works or not? Did you try to look at that?
So yes, something like QFT, where you have 2 power n elements at the leaves, CFLOBDDs do not scale very well because they cannot represent the states very efficiently. So, however, there are cases where even if it's not just 0 and 1, you have sufficiently smaller number of output values, I would say, CFLOBDDs still perform well. But if you have something like QFT, it's not that great, and hence we want to see if there are other ways that you can scale CFLOBDDs or another variants that you can try on CFLOBDDs to be able to scale to such large outputs as well.
Okay, thanks.
Yeah.
I think I might have misunderstood, but you said that the CFLOBDD remains non-looping, but when
Yes.
you reuse components in series, it seems like you're making a loop. Is it because at evaluation time you're still going through the fields in the fixed order? Is that all you need?
So yes, so during evaluation time, let's say you enter this you're trying to evaluate x0 and x1 because let's say in this case they're represented using the same function. I go to the green edge, blue edge, take the x0, come back to the blue edge because I entered through the blue edge, and then take the purple edge, evaluate for x1, and then take the purple edge and not the blue edge. So I know where I am when I'm evaluating an assignment. So that's why we don't run into loops.
Okay.
Yeah, I hope that's clear. Okay, thanks.
Thanks very much. Very interesting work.
Thank you.
You mentioned that they're plug compatible with regular BDDs, but then you said something about how you may need to rethink your algorithms. Do I take it then that they are plug compatible, it's just that you might get pretty bad performance unless you change your algorithms, or did you mean they're almost plug compatible and you do need to change your algorithms?
Okay, so by plug compatible, we mean that you can design every algorithm that a BDD does in a CFLOBDD. However, in some cases, because you're dealing with half the number of variables at a time and not half the size of the output, you would have to design your algorithms that way. There is only then would you have a more efficient algorithm for that particular operation in case of CFLOBDDs.
Okay,
Yeah.
great.
So it seems like you go from a BDD to a CFLOBDD by like finding things to merge. Is this in general, like, are you solving subgraph isomorphism multiple times every time you do this, or is there some like more clever way of?
Okay, so I understand your question. So we don't actually go from a BDD to CFLOBDD. The CFLOBDD representation is created using the structural constraints as such. We don't first create a BDD and then go to CFLOBDD.
I see.
So we don't, and we do merge subgraphs when we do, let's say we perform some operations and then we have we have this bigger uncompressed CFLOBDD, which we need to merge. In that case, we do that. We do maintain it's basically hash const. So we first create this internal, let's say internal subgrouping, and then we check if that's already in memory, and then link it to that pointer. But we don't move from a BDD to a CFLOBDD.
I see. Okay.
Yeah.
All right. Thanks.
Thank you.
One last question.
Hi. So on the slide right behind you, it says quantum Fourier transform from 16 to 1x. Could you give like just a summary of what is it that gets compressed there when it goes far down? Quantum Fourier transform, second to last line.
Yes.
From 16 to 1x over there.
Oh, it's just the number of qubits that we could scale to. So the number of qubits the CFLOBDDs can scale to in case of quantum Fourier transform is 16 bits, and the same as BDDs as well. So I guess I didn't understand the question.
So how should we interpret the? Okay, so
The number
so we're not getting an advantage for QFT. Is that roughly?
Yes.
I see. So
That's
that's
what I'm
the point. Okay.
Yes,
Got it.
yeah.
Thank you.
All right. Let's thank our speaker
Thank you.
again.